Okay, so I will repeat then briefly. Right, the Earth's formation. I think you can understand. You could understood. There was a giant molecular cloud uh, composed of dust and gaseous materials, and which formed something called solar nebula. Okay, this solar nebula was the initial status of the stage of the formation of the planet, and then this solar nebula produced some of these tiny materials concentrated or accumulated into each other, making more bigger materials, right? So these more bigger materials we call planetesimals. So these planetesimals continue to grow and make more bigger materials. So actually, these planetesimals are very tiny objects. Were formed from very tiny objects from dust materials or dust particles which were available in this giant molecular cloud. Okay, and these tiny objects were made into more and more bigger objects by physical collision, right? So this physical collision made these materials to accumulate, because with this increasing mass little by little caused some gravitational field to generate also there. Okay, so this gravitational field uh, caused some heat dissipation because of this collision, frictional and everything, every other energy sources became available at that time, and the growth of these materials, these planetesimals, happened due to this increasing gravitational field and collisions, right? So they made bigger materials little by little, so that we could find more and more bigger objects to form, right? So tiny materials like dust particles accumulated and formed a little bigger ones, relatively bigger ones, and then these bigger objects, materials collided to form more and more bigger materials. Those we call the protoplanets. Okay, those we call protoplanets, and here you can see the protoplanet, but they are not planets actually. Why we call them protoplanets is, to make them planets there should be some chemical differentiation process to happen. So I already explained about the differentiation, and this differentiation made these protoplanets to stratify, to make into different layers. For example, the heavy these are made of elements, you know. The heavier elements wanted to sink into the interior, whereas the lighter ones were floating on the top, right, on the exterior, on the surface. So originally these bulk materials were like making something like these two layers, right? The heavier ones came into the interior and the lighter ones were outside. So originally we had two layers of the earth, and this process we call the differentiation, the chemical differentiation of the earth, because this was sorting out the heavy materials like iron and nickel into the interior. That is what we call the earth's core. And then the outer materials, the lighter ones, mainly composed of oxygen and silicon. In terms of a silicate material, they were relatively lighter than the iron and nickel, as you know. So they formed another layer that we call the silicate layer. So initially we had only two layers in the earth, the core and the silicate layer. Actually, this silicate layer was called bulk silicate earth. Okay, because it was predominantly made of silicate material, silicon and oxygen bearing compounds, right? We call it bulk silicate earth. So actually this process was taking place uh, as like in an ocean, but this ocean is entirely of made of magma at the very beginning. So in a magma ocean, this floating and sinking of these materials was happening, right? So in this magma ocean, the heavy materials were going into the interior, and the lighter ones were floating. So that's what happened at the very beginning, the initial stage, the first stage that made the protoplanet to become a planet, the first stage of a planet, right? So we had the core formation and then the bulk silicate earth formation. Afterwards, this bulk silicate earth uh, layer, that means this layer was also further differentiated. So that made something called the crust and the mantle. So that means this bulk silicate earth portion was also differentiated further into two layers that we call the mantle and the crust. So the extreme exterior part is called the crust, and the intermediate or the next part in between the crust and the core we call mantle. So we have another layer, this is mantle, and the exterior layer we call the crust. So this is how the earth was differentiated. Actually, for this core to form, it took about 100 million years. 100 million years were taken place uh, to realize this process to uh, happen. And further differentiation, that means this bulk silicate earth portion to differentiate further into crust and mantle, it took about further longer period of time. Actually, it took up until 3 billion years from the present. That means Earth was formed at 4.5 billion years ago, and then another 100 million years was taken to form the crust, form the core, and then until 3 billion years old, uh, that means another 1.5 billion years from the starting time of the Earth's formation, took to generate the crust and the mantle. Okay, so by the time of like 2.7 to 3 billion years ago from present, the earth was the differentiation process was complete. Okay, differentiation means forming layers of the earth, right? So this process have continued until about 3 billion years time. So as I said, I explained all these things, the drawing on this slide actually at that time. Anyway, if you say that this is the present, okay, so we'll say this is the present 0 million years. That means today. Okay, you can use GA for billion years. Okay, that means giga annums. GA means giga annums ago, right? So from today, 4.5 giga annums ago, Earth was formed, right? 4.56 giga annums ago. That means billion years, right? Giga annums. So if something is million years, then you can make term it as MA. Okay, million years ago or mega annums ago, right? So from today, about 3 giga annums ago, right? About 3000 billion years ago, Earth was complete in terms of differentiation. Okay, so that means like for 1.5 billion years has taken for this process to complete, right? At the very beginning, Earth's accretion happened at 4.5 billion years ago, and then 100 million years took to form the Earth's crust. Sorry, Earth's core, right? Like 100 million, very short period of time, right? 100 million years took to form the core. And then after that, it took about nearly 1.5 billion years to complete its differentiation, forming crust and mantle. Okay, after that we have a completely differentiated planet, and till today Earth is facing so many internal processes and also exterior processes, external processes, reshaping its configuration, right? Earth's original shape is continuously uh, making in a different shape, right? So anyway, we have a differentiated planet now, uh, uh, from which was started with a protoplanet. Protoplanet is undifferentiated planet. Okay, once you have this layered structure, only you can call any material in the solar system as a planet. Even other planets are also differentiated in different ways. Ours, we have core, mantle, and then crust. Okay, so the core is also formed in two layers, right? Although we call it just the core, but it is still differentiated into two, right? We call it inner core and outer core, right? This inner core is made of solid iron and nickel, and the outer core is made of you can see here, solid inner core, and the outer core is made of liquid, still iron and nickel. You have it is made of liquid materials. The reason is, at the very beginning it was a magma ocean, as I said. So in this magma ocean, materials were floating inside, right? But at the very deep part, you see, about 6,000 kilometers deep in the core, at the core, radius is like 6,370 kilometers. At that depth, huge materials are overlying, right? 6,000 kilometers of mass means huge column of weight exerting at the interior, right? So everything made solid. So all these iron and nickel were solidified, were like in terms of solid, due to tremendous pressure. But outer part is exerted with less pressure, so therefore they can still remain as a liquid. Okay, so solid, liquid, two stages are distinguishable in the Earth's core due to that reason. And from there onwards, we have the mantle. Mantle is also differentiated into two portions, two parts. We call it upper mantle and lower mantle. We'll discuss that later on. But just keep in mind that after the core, we have the mantle. The mantle is also it's not entirely a solid. It's a semi-solid material. Okay, it's semi-solid. Semi-solid means you don't see the liquid properties entirely, but you don't see the solid properties entirely also. It's like a jelly, right? Something like a gel, so that you can term it as a semi-solid materials. And the extreme exterior part, very tiny section, we have as the crust. So this crust is in average like 40 kilometer thick, right? It's very tiny, I mean very thin compared to other layers. They are thousands of kilometer scale, right? They are thick relative to this crust. Crust is like 40 kilometers, very thin, very thin part, right? The crust is also divided into two, that we call the oceanic crust and continental crust, right? The oceanic crust is a thin crust available under the oceans. Continental crust, where we are standing on now, is relatively thicker compared to the oceanic crust. So in average, 30 kilometer or 40 kilometer thickness is there available for the continental crust itself. But at places like Himalayas, this continental crust extends further, like 70 kilometer thick scale. Oceanic crust is in an average like 7 kilometer thick, but in places like in the Mariana Trench, where very deep oceanic crust is available, like 11, 12 kilometers thick. Okay, so anyway, in average, you can consider crust is up to 40 kilometer from the surface. Surface is 0 kilometer. So we are starting measuring from there onwards. So it's like 40 kilometer thick crust in average we have, right? Both oceanic and continental, right? And then from there onwards, we have the mantle, as I said. So this mantle can extend up to very deep, up to 2,890 kilometers. That means the place where you meet the starting point of the core, right? That is actually the outer core. Starting outer core, up to that, we have the mantle. So this mantle also we have as two layers. Later we will discuss it further, upper mantle and lower mantle, right? So basically we have the crust, then mantle, and then outer core, and then inner core. This is how the earth was formed. This is what we call the differentiation, earth's differentiation, forming crust layer and mantle layer and core layer. So this stratification make any object or the planetary material or the protoplanet to be called a complete planet, right? Unless the differentiation is completed, we can't say that object as a planet, right? So is it clear, that section?
Yes, it's clear.
Okay, so
Yes,
this Earth's structure, we can I can make equivalent to an egg, because we have a shell in the egg, which is equivalent to the crust, right? You can just see it's very thin, right? The crust is very thin in the egg. I mean, the shell is very thin, so which is equivalent to the crust, and the egg white you can equalize to the mantle, because you see it's not entirely a solid, and also it's not entirely a liquid also, but it can deform. You can change the shape, right? You can make different shapes, shaped of, I mean, you can change the shape, its original shape. uh, it's like a jelly like material, right? So that is mantle, and then you have the yellowish yellow part as the core, but only difference is you don't have the inner core solid material there in the egg. That is the only difference. uh, this is the general structure. So compositionally, we have crust, mantle, and core, because the material that the chemical properties or the chemical materials that compose these three layers are compositionally different, right? So that's why we term these layers compositional layers, right? So you can call this crust, mantle, and core layers as compositional layers, because you see the core is entirely made of nickel and iron, right? Elemental nickel and iron. And the mantle and crust are entirely made of silicate materials, right? Silicon and oxygen bearing compounds. But still, there are some differences in these chemical differences in this crust and mantle also, although they are made of predominantly silicon and oxygen. Because in the mantle you have a lot of iron and magnesium rich silicates. Okay, iron magnesium rich silicates, they are not elemental iron and iron like in the core. They are just natural elements, iron and nickel, elemental native elements. But the mantle, you still have iron, but yeah, in the form of silicates, iron silicates and magnesium silicates. Okay, so therefore that composition is different from the core. And how that differ from the crust is, still crust is also silicate, like the mantle silicates, but the crust is predominant in aluminium, right? Not iron, magnesium. It's enriched in aluminium. So therefore, you call the the crustal composition as Cl, SiAl, right? What you mean by that is silicon and aluminum, predominant uh, components, right? Silicates, mainly aluminum silicates. So that's why we call it Cl. But for mantle, which is also silicate, but predominant in magnesium and iron. Actually, the magnesium component is much higher than the iron component. So therefore, uh, it's called SIMA, right? Cl SIMA. You can call it SIMA because it's made of silicon and magnesium. Okay, so Cl and SIMA is just a shortened form to understand the chemical difference between these two. So therefore, we call them compositional differences in these layers, compositional layers. The same type of layers can be there in terms of spheres, because the Earth is a sphere. So therefore, these layers are also spherical, right? So you have different layers, but these layers, you can categorize them into different layers. Spherical layers, which we term as rheological differences, rheological layers. Rheological differences means their properties are different, their mechanical properties are different. Mechanical properties, how they behave under forces, mechanical forces, right? Not the chemistry, but mainly based on the physical properties. So therefore, we call them rheological differences. The solid the differences available under the mechanical changes, right? So we have three layers. We call lithosphere, then we call asthenosphere, and we call another layer mesosphere. So the most interior uh, part, actually, we call lithosphere because it is made of entirely rocks. Litho means rock. So actually, from the mantle onwards only, we term them these rheological differences, because the core we don't take as a rheological layer, but you can still take because you have only the elemental things there. The iron and nickel there, but this difference you see here, mesosphere, it's entirely made of uh, elemental iron and nickel. So therefore, it can be entirely taken as a single layer, as the mesosphere. And then you have the asthenosphere, because in the asthenosphere, uh, we have a lot of uh, what do you call, some vigorous convection forces, right? Convection, right? It's a mechanism of heat transfer, right? Convection is a mechanism of heat transfer. So some kind of some flow patterns are there, heat flow patterns are there. So they are uh, constantly, the materials are rising and going down, okay, circulating, right, like this. So we call them convective cells, right? Convective cells are there in this asthenosphere. So therefore, that layer is a separate layer. Physically they are behaving differently, that's why we divide it into different layers. So mesosphere is there, and then asthenosphere is there, and then we have the lithosphere. The lithosphere is just the solid rocks. There you see the extreme exterior part, we can term as a lithosphere, because we have solid rocks in the crust and solid rocks in the upper part of the mantle. So we didn't discuss much about the mantle difference, mantle two layers, upper mantle and lower mantle. But remember, the upper part of the mantle is entirely made of very robust solid rocks, right? So therefore, this lithosphere combines the crust and the upper part of the mantle, right? So therefore, you have one separate layer which is entirely solid. That is lithosphere. Litho means rock in Greek terminology, I think. So therefore, it's a spherical anyway. You can see the spherical shape. So therefore, it is called lithosphere. And then the below the lithosphere we have the asthenosphere, because in the asthenosphere we have the constantly flowing materials due to convection heat transferring process. You see, when you boil a kettle of water, right? You can boil a kettle of water, uh, and you can put some ink drops there, right? While boiling, you will see these ink drops floating in a circular manner, right? In a circular manner like this, right? From high heat to low heat areas, right? This is what we call the convection. Actually, this is heat transferring, but this heat transferring is accommodated with material transport also, right? It is not an entire, it's not like water flow, right? I mean, flowing water is another transferring of material mechanism, but this is just from high heat to low heat, right? Or high concentration to low concentration, something like that is what we call the convection, right? Convection type of heat transfer, right? This heat transfer is also accommodated with material transfer. So that's why you see these ink materials are also moving along with this heat transfer, right? So similar to that, you can observe in the Earth's mantle also this flowing mechanism, right? So therefore, that part we separate into a single sphere. That is what we call the asthenosphere, right? And then we have the mesosphere down there. Okay. Right. So uh, yeah, even after this lithosphere, you can have other spheres like atmosphere, stratosphere, like that, right? So you can have external spheres also. These are internal spheres, right? So anyway, the main units of the Earth is composed of like this. Compositionally, you can term them crust, mantle, and core, but rheologically, you can term them lithosphere, asthenosphere, and mesosphere, right? These are the categorization of these spheres of the Earth. Okay, right. Before going into further discussion, is there anything that you did not understand? I will share this recording later on, so that you can go through again and see these figures also in detail, and get further understanding. And just to pay attention to the depths also. You see, the crust is, you can, in average, we consider the crust is like 40 kilometers, right? From there onwards, you can have the mantle. But in places, I said the crust can be go like 70 kilometers. And actually, there are some places in the Himalayas, even if you take to the roots of the Himalayas, actually it extends up to 100 kilometers like. So therefore, this the crust, some in some diagrams you might see 100 kilometer as its thickness due to those extreme places. Otherwise, the average thickness is like 40 kilometers. Okay. From there onwards, you have the mantle, uh, the extreme upper part of the mantle. You see here some dark layer here, right? That is the uppermost part of the mantle, and then you have the lower mantle, and then outer core and inner core, right? So lower mantle and outer core, and then inner core, right? So these depths are changing, different depths are there. So you can pay attention to these depths carefully. Okay. So we have the lithosphere. It is very cold, right? I mean, it's like room temperature is 30 degrees, 40 degrees, like Celsius, right? That's why we call it cool and also rigid, right? Rigid means it's very robust, right? Because of when the rocks are cool, they become very well solidified. Otherwise, they are flowing. The rocks can flow, right? That's what we call the magma, right? Magma is very hot, right? Hot rocks are liquid, cool rocks are solid. And these cold rocks are brittle also. That means they can be easily broken into pieces, right? That's the brittle feature, right? But if you take the asthenosphere, which is hot because of heat transfer, as I said, the convective heat transfer is there, so it's hot, still hot. It's not cold. And once the asthenosphere cools down, you can see the crust formed out of that. Uh, that is robust or brittle. And this asthenosphere being hot is weak. It's very weak because like a semi-solid, right? We talked about that already, right? It's composed of mantle. It's semi-solid. Therefore, it's weak. It's not strong. And also plastic. What do you mean by plastic? You can change its shape easily, right? If something is deformable, that material you can call plastic, right? So this asthenosphere is also same, that can be changing into different shapes and if an external force is applied there, its shape can be changed. So that is what you call the plastic behavior. And then you have the mesosphere. Uh, it's also hot, but also stronger due to high pressure, right? Not because of other thing. It's due to high pressure. It's stronger because you see some hundreds of kilometer depth, thick rocks layers are there overlying the mesosphere, right? So it's just some hundreds of kilometer, and then if you go more and more deeper, some thousands of kilometer, right? It's like you are diving into water, right? At the shallow depth, you don't feel any pressure much, right? But if you go deeper and deeper in the water column, because of the overlying depth of water, the weight of this water column makes you very pressurized in the deep ocean, right? If you try to dive into the deep ocean, you will feel very difficult, right? Without oxygen you can't survive, right? So similar to that, this rock columns also exerts immense pressure. So therefore they are also robust, but due to pressure only, not because of the material itself made of, right? It's just nickel and iron. It doesn't mean it's strong just as elemental form, but if you melt it and solidify, then of course iron and nickel will make very strong robust material. But it's some kind of a processed uh, scenario. But here it's in the natural form, but due to pressure it is very strong, right? So this is how you can understand the structure of the earth. So we discussed about the formation of the earth, the accretionary the earth's accretion. That means the formation of the earth. Uh, so then we discuss about the compositional differences or the compositional contrasts of the earth's layers, crust, mantle, and core. And then we talked about the rheological layers or rheological differences of the different earth strata. Right. So I think you could understand of these basic aspects of the earth, and then just we will see the nature of the crust also, right? So you see here the segment of the crust is shown here in this diagram, right? So I said the crust can be divided into two. Right, see here, oceanic crust and continental crust. So two segments can be found in the crust. So it is like here, because we have oceans on the crust, right? We have oceans here and we have continents. So that's why we have two types of the crust, right? Two categories. So oceanic crust, as I said, is not very deep. it's like 7 kilometer in average, as I said, right? So this is the oceanic crust. You have oceanic crust depth, and then we have the continental crust. Continental crust is more thicker. In average, you can have it 30-40 kilometers. The oceanic crust is just like very thin, right? It's like 7 to 10 kilometer in average, right? Except for the places like Mariana Trench, it's 11-12 kilometers. Unless oceanic crust is like 7 kilometer in average, 7 to 10 kilometers. So so the continental crust is more thicker. You can see it can extend up to even 70, even 100 kilometers if you count the roots also. The roots are here. Okay, right. The boundary between the crust and mantle, right? The boundary between the crust and mantle, right? So you have the crust, and then the mantle starts from there onwards, right? Here. So this boundary, this is the mantle, and boundary is here. Okay, the boundary is here. We call that boundary moho, right? Actually, this is a discontinuity. We call it as a discontinuity because this is determined using the sound waves. Okay, when sound waves or the seismic waves, actually it is the seismic waves. We call not exactly the sound waves, but seismic waves. When the seismic waves are sent from the surface to the bottom, to the interior of the earth, there is a place where the velocity of these sound waves change, right? For example, within the crust, sound waves go without changing its velocity, but at a certain point, it changes its velocity, right? So uh, this place scientists have identified as a physical contrast, right? As a physical contrast, so that it is termed as the boundary, which you call the moho. Actually, this moho means uh, a name after the scientist who discovered this difference. Discovered this difference means discovered this seismic wave velocity difference, right? He's called Moho. His part of his name is Moho. Mohovisic, right? So this is called Mohovisic discontinuity. So it is because of the physical contrast existing between the crust and the mantle, right? This is how people discovered the Earth is stratified. The Earth is stratified due to, people indirectly discovered first that there should be some physical contrast in the Earth. So this is how they discovered first, right? So this boundary is called Moho or Mohovisic discontinuity. From there onwards, only we consider the mantle is starting. Okay, from there onwards, people consider the mantle is beginning. Okay, so there are physical layers showing these contrasts in uh, seismic waves velocities, in terms of seismic wave velocities. Okay, right. Again, in another diagram, I'm going to show you these differences. Continental crust, and this depth is there. Then oceanic crust you have with oceans. So this is the extreme outer layers of the earth, and then you have the mantle from there onwards, right? So we term it as compositional layers, and we term it as mechanical layers, right? Lithosphere, asthenosphere, mesosphere. Okay. Uh, This particularly this sonosphere is made of semi-solid material. That means it can flow, right? It's not a total liquid, although it can flow, but we call it a semi-solid material. Even mesosphere can show semi-solid behavior because outer core is a liquid, right? Okay. So these are the two types of layers, and we had this lithosphere, asthenosphere, and mesosphere. So lithosphere is the strongest layer. That means, it's very solid, right? Made of entirely rocks. That's why it is termed as litho, right? Litho means rocks, rocky layer, right? It can go up to maximum of 100 kilometers, and this is the layer that makes the plates. So you may have heard about the plates of the earth, right? That makes earthquakes, right? Earthquakes are made of due to uh, collisions of these plates, because these plates are moving. You remember the asthenosphere is a semi-solid. So on this semi-solid material can always move, that can float, like, right? On top of that you have these plates, right? The lithosphere, right? This lithosphere is made of plates, as now I told you, and these plates are movable on top of this asthenosphere, because asthenosphere can be flow, it has the flowing characteristics. Anything which is lying on top of a flowing material can take away. The solid materials can be taken away by these flow currents, right? So these flow currents make these plates to move. That's how these plates collide. Because of these movements here and there, they are moving, and they can collide with each other due to the movements of this asthenosphere. Asthenosphere is driven by the convective forces, as I said before. These convective forces carries all these plates also on top of that, right? So these plates can move due to these convective forces, and another place, this another direction, maybe another plate is coming along with this convective forces. So these two plates can meet somewhere and finally collide each other. That is how the earthquakes are happening, right? So the crust is always made of plates. So we'll discuss these processes later on. We are still discussing about the structure. Okay, the Earth's processes are another lesson. So we will discuss them later on. Okay, so asthenosphere, remember, it's a weak, ductile layer, right? Beneath the lithosphere. We have it beneath the lithosphere. And then we have the mesosphere, which is starting with the mantle beneath the asthenosphere, because asthenosphere is only the mantle part which contains the convective forces, right? All the mantle does not flow as convective forces in terms with the help of convective forces. Only the upper part of the mantle which flows. The lowermost part of the mantle does not flow because the convective forces are not available in the lower part of the mantle, right? So here, the lower part of the mantle does not have convective forces. So therefore, it is still considered as part of the mesosphere. Okay, so the mesosphere is component the asthenosphere and the outer and inner cores, right? So mesosphere is a combination of layers of the lower part of the mantle below the 400 kilometer depth, and of course it includes the core, outer core and inner core also. Asthenosphere is the upper part of the mantle. Actually, that is we call the ductile layer of the mantle. So if you can remember here, we have the mantle here. The upper part of the mantle is the one which is flowing due to the convective forces, right? So this part, and from there onwards, the mantle does not flow. So it is a part of the mesosphere here. Okay. So that's why we have the mesosphere like here, right? So mesosphere here we have, and then we have the asthenosphere, okay? And then finally we have the lithosphere, right? Very shallow part we have as the lithosphere. So lithosphere is entirely solid. It is part of, it is making the plates, the crustal plates, which are floating on top of this asthenosphere, because asthenosphere is flowing, taking all these plates also, solid materials also, right? So we have lithosphere, asthenosphere, and mesosphere, right? Those are rheological classification. That's why we call it rheological classification, because of the mechanical properties of those materials, right? Not the compositional, right? Don't get confused. Always remember their chemical features and physical features. Based on that, this earth structure definition is given as the main units. Okay, so any question up to now? What do you call, what do you mean by ductile? So you have a term here, ductile layer. What is ductile layer? Ductile means you can easily change the shape. Okay, it's a plastic behavior. Actually, it's a plastic behavior. But once you change the shape, if it can come back to its original shape, right? That is ductile, right? For example, you can change the shape of a semi-solid material, right? You can draw it, right? For example, copper wire, right? It has the ability to extend. That is ductile behavior, okay? If it is breaking, then it is brittle behavior, right? So if you try to draw a copper wire, and at a certain place it will break, right? So then it from there onwards it behaves as a ductile material, right? So this is the property difference in these properties, okay? So lithosphere is not ductile actually, because it's easily deformable. But under high temperature, lithosphere can also behave as a ductile material also. But I think you don't need to consider that right now. I will discuss that when it comes to petrology or learning about the rocks later on, right? But for the time being, you just remember brittle means breakable, ductile means the shape can be, the geometry can be changed, geometrical shape can be changed, okay? Right, so if you have any questions. If you have any questions, you can just ask, because now it's almost 10 o'clock, but I have a small content to continue. Maybe 10-15 minutes, I think you can bear. Is that okay?
I think
Are you okay if we continue another 10 minutes or 15 minutes?
okay, okay, sir.
Yes, okay, sir.
Okay, right.
Yes.
Yeah, because we started at about 8:15, like. Yeah. Okay, so let's move to the some kind of elaboration about the crust, the Earth's crust. As I said, we have oceanic crust and we have the continental crust. So where we are standing now is the continental crust. So basically the continents represent the continental crust, oceans represent the oceanic crust, right? So what is happening in this oceanic and continental configuration is we can discuss under Earth's processes, because the material that composes this oceanic crust and continental crust makes them some natural processes, okay, to happen, right? So anyway, let's see first the crust that makes up the ocean floors. As I said, is oceanic crust, and it is entirely composed of a material called basalt. Okay? Something called basalt. Actually, this basalt is a rock name, right? It's made of magma, but it has a special kind of specific composition, right? This basaltic magma is coming out, that is what we call the extrusion, right? Extrusion, or it is extruded at mid-ocean ridges. Do you know mid-ocean ridges? Have you heard of about mid-ocean ridges? There are, you know, the mountains, right? Like here, you have the mountains, you know, Piduru Talagala, Nakas, so Himalayas, Everest, Alps. All these are mountains which we can find on the continents, right? Continental crust. Actually, there are mountains on the ocean also, right? In oceans also, there are mountain ranges like this, right? Like you have the mountain range here, right? This is a mountain range in the continent. Similarly, you have mountains under sea, right? You can never see them unless you go down into the ocean floor, right? So these are called mid-ocean ridges. Actually, these mid-ocean ridges, at these mid-ocean ridges, there is magma flow, right? So magma is coming out and dumped at the ocean, right? There are places like that. So these places are called mid-ocean ridges, okay? At these places, this specific rock type, basalt, is found, right? In continents, also we have the magma flows, right? That's why we see volcanoes in places, right? Basically, we see not basalts, we see some other rocks. We call them granites, right? You see, I think you know granites, right? So granites are formed in continents, but basalts are formed in oceans, right? This is one rock type, basalt. So their chemical composition is entirely different, right? Its chemistry is entirely different. So that's why we have different names for those, although they are just magma. For an ordinary person, it is just magma, right? Magma forms a rock. It is just a rock, right? But their chemistry is different. Their magmatic chemistry is different. So therefore, ultimately, they produce different types of rocks, right? So in mid-ocean ridges, you have this basalt formed, and this basalt makes ocean crust a dense uh, layer, right? Compared to granite, these basalts are heavy. Heavy means they are having high density minerals, because they are mostly composed of iron and magnesium rich phases, iron and magnesium rich minerals, right? In the mantle also, I said iron and magnesium silicates are dominant, right? But these basalts, again, we have iron and magnesium rich minerals, but not as dense as the mantle itself. Okay. Later we will discuss about their chemistries also, because you know, gems are produced from rocks, right? So you have to learn about the rocks, the scientific aspects of the rocks. That's why you are having a geology course at the very beginning. So you need to know the basic principles of Earth's formation, and then what type of rocks you have, like that, right? Then only you can understand about gems, because gem is another kind of a mineral, right? So minerals compose rocks. Actually, elements, you learned the periodic table. Elements, when it is formed in different compounds, chemical compounds, they can make minerals, right? So then minerals altogether collectively can form rocks, right? So this is how the earth is formed. So gems means one type of a special category of minerals, because all minerals, you can't say gems, you can't sell them. I mean, you can find many minerals everywhere. When you walk, you can find several minerals, hundreds of minerals on the Earth's surface, but you can't sell them. They are not valuable. I mean, economically, they are not valuable, right? But you have concentrated deposits in gems in some places only, right? Why is that, right? So you have to understand, right? So specific properties are there for gems to make them precious, right? Valuable. expensive, right? All minerals are, for example, you have quartz, right? You know quartz, Tiruvana, right? You can find everywhere, but you can't sell them at a good price, right? But of course, if you find very pure quartz, then you can sell them as a gem, right? As a semi-precious gem, you can sell them. But the value depends on its quality and its durability and its beauty and everything, right? So that's how we define gems out of the minerals. You know how many minerals are there in the world approximately? Any idea? In the planet Earth, how many minerals have been discovered approximately? Just a guess. Can somebody tell? Is it tens or hundreds or thousands or how?
Like around 5,000 something.
Well, yeah, some thousands, right? Around 3,500 minerals have discovered as known minerals. There may be some other, a lot unknown yet, right? About 3,500, you can expect minerals are there. Out of that, how many gems, gem minerals you can find? 3,000 minerals means 3,500 means including gems, gem minerals. Do you know how many gems discovered? I mean, defined as precious and semi-precious, like varieties, at least. Any idea? Out of,
Low than 100, so
yeah, something like that. 150 like gems are available, right? Uh, Either semi-precious or precious. About 150 varieties can be found approximately. Okay. So in geology or in gemology, right? You are learning to be a gemologist. That means gemologist is also one of the scientists, right? So actually, we are used to call gemstones, right? We are used to call gemstones. Stone is a rock. Stone means rock, right? But gem is not a rock, right? So that means we are loosely using the term, scientific terms, right? But gemstone, why we use it is it looks like a stone, so that's why. But it is actually a mineral. It's a single mineral, right? It's not a rock, right? To tell to call something a stone, it should be a rock, right? But we use it traditionally. Actually, it is a commercial term, right? It's not a scientific usage. So as a gemologist, you can call them gem minerals, right? Not gemstones, right? Okay. Anyway, it's another something else. So let's see. The oceanic crust is made of these heavy minerals, right? Heavier type of mineral compared to the continental type. So therefore, oceanic crust is more dense than the continent. So when these two, because I said they are plates, right? You remember the crust is made of plates, right? All these crust is made of pieces of plates. So this is lying on top of the atmosphere. They are floating, right? So when these plates are floating, when they can meet two plates because of convection currents, you remember the mental convection currents, if they are flowing in two directions, what happens if two convective forces are there, right? Like this, right? We call them convective cells, right? Convective cells. So in places like here, one plate due to this convective force can move in this direction, and another plate due to this convection can float in this direction, opposite direction. So they meet together and collide together, right? So before collision, actually what happens is, if this is an oceanic crust, if this is an oceanic plate, right? And if this is a continental plate, due to density contrast, what can happen? This heavier one can sink or subduct beneath the lighter one, right? When they meet together, the heavier one definitely go down, right? So this is happening. So this is we will discuss these things under Earth's processes. So anyway, the point here is oceanic crust is heavier, dense, more dense. So it's mainly composed of heavy material, that is what we call the basalt. But the continental crust is made of granite-like material, which is lighter because it is composed mainly of aluminum-rich materials. Okay, aluminum-rich materials. So that's why that is less dense. So usually the granite is, the density is like 2.7 grams per cubic centimeter. Uh, the basalt is less than that, 2.4 like. Okay, and also even though continental crust is much thicker, like 70 kilometers or 100 kilometers, it is lighter because of this density difference, right? This is just 7 kilometers thickness, but it is dense, right? It's more dense than the continental crust. So therefore it can subduct beneath the continental crust when they meet together, right? So once they collide, these are earthquakes and those things are happening, right? Volcanoes are generated due to this subduction. Actually, this subduction causes the forced uh, moving, so that under friction, so here we have a lot of frictional forces acting, and it generates extra heat, and this heat causes the continental crust itself to melt, right, due to this friction. Because these are 1,000 kilometers, some thousands of kilometer thick, sorry, thousands of kilometer wide plates, right? So they are moving down, so they can produce huge amount of heat by friction, right? So some magma is generated and it comes out as a volcano, right? This is how volcanoes and some earthquakes can produce in this type of places. We call them plate margins. The Japan islands is along a plate margin like here, right? Japanese islands are located somewhere here like this, right? So Japan is always experiencing both volcanoes and earthquakes because of this reason. So anyway, the oceanic crust is more thicker than the continental crust. Okay, right. So we have the mantle. Then the second layer, we call the mantle as having some convective forces. Remember, it's part of the asthenosphere, the upper part of the mantle. So the beneath the crust, exactly, we have the mantle. So you see here, asthenosphere is flowing like this, right? These are the convective forces. So these convective forces, because of heavy high heat available there, uh, I will discuss about the heat availability. So briefly, I will tell. At the formation of the Earth, you remember there was a lot of gravitational collisions. So this collision made a lot of frictional heat to accumulate there. So Earth's accretion itself was a hot process. That's why you had a magma ocean there at the beginning. So that heat is still there in the Earth's interior, right? So not only that, but you see, once you had the heat source, gradually it should cool, isn't it? Now it's 4,500 million years. So why Earth is still hot? Can't you expect the Earth should be cool now? It has elapsed this many years. Why it is not cooling? So if something is cooling, and at the same time, if something produces more heat also now presently, so this cooling process is disturbed, isn't it? So cooling is happening, at the same time heating is also happening, new heating process. That is what we call the radiogenic heating. So you may have heard about the radiogenic process. Maybe we will discuss about this radiogenic process later on if we have some time. Actually, this is again related with elements, isotopes, right? Producing isotopes, that means different masses, elements with different masses causes heat dissipation, heat production. Okay, uranium, thorium, and potassium. these three elements can produce heat due to their radiogenic processes, right? So this radiogenic processes takes place uh, in long periods of time. Some processes, for example, it takes some hundreds of million years for uranium to decay into, to produce heat and convert into a new mineral, sorry, new element. For example, lead. Uranium can produce lead, but to produce this lead, it has to dissipate heat, right? In terms of alpha rays or gamma rays, right? They dissipate heat, and this heat, with time over the millions of years now since the Earth's formation, is accumulated inside the Earth. So original heat that was available at the accretion, although it's dissipated and cooled, this new heat production due to radiogenic heat production uh, accumulates more and more heat. So therefore, our Earth is still hot. This heat causes mantle heating, and that heat is available as convective forces here. Okay, so this heat is constantly available at the interior, so that causes this material to flow. So some crustal plates available, right? So these plates are moving because of that, right? So these plates are moving because of this heat transfer that creates a dragging force, right? Pulling and pushing like forces are happening at the upper part of the mantle, right? So this is the upper mantle, right? This part is the upper mantle and this part is the lower mantle. So in the lower mantle, we don't expect or experience this type of convective forces. So that's why it is taken as part of the mesosphere together with the core, right? The upper part of the mantle together with the crust we take as the asthenosphere, right? So we call this heat flow as the asthenospheric upwelling. That is another term that we use for this convection, upwelling. Okay, asthenospheric upwelling, because this heat is coming from bottom to top. So that's why we call it upwelling, right? So this asthenospheric upwelling causes all these plates to move here and there, right? So we will discuss that under Earth's processes in detail. So anyway, now we'll see the mantle. It contains rocks made of denser material, more denser material, right? So it's entirely made of iron and magnesium rich silicates. They are more denser than the basalt that we discussed, which is available at the ocean floor, right? It is denser than the granite anyway, basalt, but the rocks that contains in the mantle, which is called peridotite, are more denser, right? They are very heavy. So these materials are made of iron, magnesium, and calcium actually. So calcium is also forming a part of this peridotite materials, right? You can call it peridotitic mantle also, because it is composed of the rock name peridotite, right? You may have heard a gem variety called peridot, right? You remember the greenish gem? That is peridot. Why we call it peridot? Actually, it is not, peridot is derived from peridotite, because the peridotite, the rock type, is predominantly made of the mineral called olivine. Okay, there is a mineral called olivine. You know that it's also considered as a gem. So this olivine mineral, when it is taken as a gem, you call it peridot, right? Because it is coming from peridotite rock, right? Olivine is a magnesium silicate, right? It's entirely magnesium, and also iron is also there. There are two varieties: magnesium rich olivine and iron rich olivine, fosterite and phyllite. That's why it is called peridot also, right? Anyway, olivine is a dense mineral which is available in the mantle, right, composing most of its rocks. Okay, so this is about the composition of the crust and mantle. So we will discuss more details about the structure, and then we will move to the processes, Earth's processes, in the next time. All right. So do you have any questions? Did you type your numbers? Oh yeah, yeah. You put your names, right? Okay. Okay. Do you have any question? Okay. Anyway, so please share your details. I mean, your if you have your institution details and your company details or websites or whatever, so that everyone can share them and interact with each other, because you all may have not met each other, right, yet. Have you come to PGIS before? I mean, for a lesson, physical lesson? Has
Yes, sir.
anyone?
Yes, we came one day. 6.
Okay. For a class you came, or I mean, as a batch you came?
Yes, yes.
Okay.
We have met in the inauguration programs in the 6th of
Okay.
January, and we
I
had a
see.
class from Professor Navara.
Yeah. All the courses, I think. Okay. Right. So anyway, so we will stop here for today, and we will meet most probably next week.
And excuse me, sir, how can we get the slides of the lecture?
Yeah, I will share them later on.
Okay,
Right.
okay, thank you,
I
sir.
will share them. Maybe Dr. Dharmapriya will send you the link for
Okay.
to access them. Okay, so I will stop here for today then. Have a nice day.
Thank you, sir.
Have a nice day, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.